Birds are by far one of the biggest inspirations when it comes to aircraft design. But just how much is the industry actually looking at them? Stay tuned. Some of the very early aircraft designs were much more inspired by birds than today's are, to varying degrees of success. But today I would like to highlight a few of the most obvious things about birds that doesn't seem to have made it into our aircraft designs yet. And I'm emphasizing yet here because some of these features might actually be on their way into coming designs, but let me first point out one thing that will not. Despite many early attempts, mechanically operated flapping wings never really took off. And the reason for this is that because of the size of the muscles or motors required in order to produce enough flapping power to get a machine like that airborne, even with just a single passenger, would be enormous. If a human would try to fly using wings like a bird, it would need a wingspan of around 7 to 8 meters or 25 to 30 feet. And that would require pectoral muscles attached to the keel bone, which would have to be, well, huge. Some estimate that it would have to stick out as much as 1.25 meters. Not that I'm suggesting that we try to evolve that ourselves, but even mechanically operated muscles would have to be enormous compared to the weight that they would be able to lift. Now there have still been attempts of this, of course. Back in 1894, Otto Liljendahl, famed for his success with gliders, built an ornithopter. That's the term for an aircraft running on human power alone. But sadly, his untimely death in a gliding accident then put a stop to its development. Since then, there have been various other attempts with varying degrees of success, but all limited in their application. The most recent that I know about at least was the 2005 attempt from Yves Rousseau, who succeeded in flying the grand distance of 64 meters. But I should also point out here that this was on his 212th attempt, and sadly on the 213th he suffered a life-changing accident. But that's enough background. What we can say with some confidence is that we aren't going to see flapping wings on commercial aircraft anytime soon. And before anyone points it out, that goes for the Boeing 777X as well. Because while its wings can fold and unfold, that ability was created to allow for a greater wingspan and lift, while still ensuring that the wings can fit into the smaller stands of the original 777. So not much flapping. No, instead, it's much easier, as early aviation pioneers also discovered, to use some of the bird's other amazing features, like the ability to glide using the lift produced by the wings rather than to try to continuously flap. Actually, if we think about it, birds really only tend to do that to get airborne and propel themselves, and that's something that our amazing jet engines do quite well for us already. But what about other features of birds' wings, like their feathers, for example? Well, as it turns out, feathers are actually really clever. They aren't just there for insulation. Instead, they actually aid a bird's flight by adjusting automatically to changes in the airflow, which helps the bird glide and control itself in the air. Of course, no aircraft has ever been covered in plumage, and nor are they likely to ever be, since that would increase their weight significantly. But if you take a look through the window at, say, a Boeing 787's wing when it's bumpy outside, you might notice something quite interesting going on. The 787's wings have multiple spoilers on its upper wing surface, and in gusty conditions, specifically during vertical gusts, these spoilers actually do act a little bit like feathers. Accelerometers and sensors on board monitor the vertical changes, and those inputs are then fed back into the autopilot system, which adjusts the spoilers to suppress or alleviate the motion which would otherwise be caused by the gusts. It's pretty clever, actually. But when it comes to wing design, one of the biggest ongoing challenges is that they have to work efficiently throughout all phases of flight, and every phase has different requirements. Takeoff and landing require great performance and lift at low speed, while cruise requires efficiency at high speed. And if we start getting into supersonic versus subsonic flights, well, then the differences are even bigger. So a lot of innovative concepts are now coming out, focusing on how to develop wings that are less of a compromise for each phase and instead more efficient for every phase. And that brings us to Up Next, a project focusing on exactly this type of wing design. It involves a Cessna Citation 7 bizjet, which has had its standard wings replaced with some brand new ones, intelligent ones in fact. This intelligence comes from a high aspect ratio design with semi-elastic movable tips able to adapt to the movement of the air. Alright, I know that birds don't have elastic wings, but their wingtips do tend to be movable. Anyway, this citation will also be fitted with a LiDAR system, where LiDAR stands for Light Detection and Ranging. This system uses light in the form of radar pulses to measure ranges, and this helps it to build up a very precise 3D model of the air the aircraft is about to fly into. The fundamental difference between a standard weather radar and LiDAR is the use of light or infrared instead of radio waves. And this means that the LiDAR is more able to spot turbulence, since it provides something vaguely similar to heat sensing. That's great in this application, because it means that the aircraft can start to automatically adjust the wing shape to adapt to the detected turbulence proactively instead of reactively. This will potentially make it even more efficient in taking advantage of those vertical air movements than the Boeing 787 example that I gave you before. Now you might be wondering why not all aircraft is using LiDAR instead of standard weather radar, but normal radar has a much greater range in terms of conditions and distance. And since that's what's required for weather detection, and that's why we normally use the radar, that's why we're using it, and it's also significantly cheaper. Anyway, another bird, a bird of prey in fact, which aviation and especially Airbus has been closely studying, is the owl, specifically the common barn owl. Now, it might have a common name, but its feathers are anything but. You see, the common barn owl and some of its fellow owl friends, including the long-eared owl, have very uncommon feathers who are kind of serrated like a comb. So why is Airbus so interested in that then? Well, it turns out that the serrated edge has a big impact on turbulence because it helps smoothing it out, or at least break it up into smaller pieces. The trailing edge feathers, which form the serrated edge, help change the angle of flow of the air coming over the wing, and this effectively directs the flow into many smaller, more stable streams. These airstreams are then dampened by a further, secondary layer which reduces the sound. For an owl, this means that they can be very quiet and sneak up on their prey, but for an aircraft it would mean a more stable boundary layer off the edge of the wing, making it more stable and efficient. The serrated edge also has a second effect, allowing the owl to dive down very steeply and then quickly being able to change over to produce lift in order to climb away again, without needing to flap its wings. This is made possible because the air remains stable, enabling the wings to produce lift even with a large and sudden change in the angle of attack. So the aerodynamic qualities of an owl's feathers are being studied to see how they could be integrated into aircraft design to deal with both turbulence, boundary layer separation and general aerodynamic efficiency. This might actually also be helpful in dealing with another major issue for aviation: wake turbulence, and I'll explain exactly how soon. But while we are on the subject of issues, I would like to highlight a tool that I am using to solve several of my own, and that's today's sponsor, NordVPN. I love using Nord because they provide a quality product that does exactly what I need from it. Nord enables me to get access to geo-blocked research material from all over the world by virtually moving me to the regions where the material is available. And it also lets me watch my favorite TV shows and sport events from Sweden even when I'm at home here in Andorra. But the best part are NordVPN's security features, which keeps my browsing private and secure, especially when using public Wi-Fi in hotels, airports and restaurants. And they now even have features that can scan emails for malware, block ads and loads of other things. It's quite impressive really for the price it costs. And when we're talking about costs, if you use Nord to virtually move around to different countries when you're planning a trip, you can find quite different prices on things like flights, hotels and rental cars depending on where you book from. And that can actually save you quite a healthy buck. Just remember to clear your cache before each search. Anyway, I am so happy to announce that if you use my link here below, which is nordvpn.com/mentor now to sign up, you're not only supporting me directly, but you will also get 4 free months, which makes this deal even better. And as always, you can test it completely risk-free since Nord always gives you a 30-day money-back guarantee. Thank you, Nord. Now, where was I? Yes. Wake turbulence and induced drag is a big challenge in aviation, and it's biggest when you have a big wing who is producing a lot of lift. This, by the way, is why aircraft have to take off and land with a certain separation, because the majority of wake turbulence is creating during these two phases, when the aircraft are moving relatively slowly but also producing huge amounts of lift. I've actually made a video specifically about this if you want to learn some more about it. But as a quick summary, it is created because of the difference between the higher pressure below the wings, where the air is flowing slower, and the lower pressure on top of the wings, where the air is flowing faster. Since that high pressure under the wings will always want to move towards the lower pressure in order to equalize this difference, you will get these huge swirling vortices by the wingtips. And if another aircraft would end up inside of one of these vortices, especially after a large aircraft, it could mean a very bad day, which I'll soon get to. Now, most aircraft today have some form of wingtip or winglet design onto their wings, and the purpose of these is to try and increase the overall aspect ratio of the wings and therefore also reduce these vortices. But this is much more about reducing drag than it is about reducing the wake for anyone behind. A serious wake turbulence encounter can result in an aircraft banking in excess of 30 degrees, and it's often the rate of bank that causes problems, including injury to anyone not strapped in, and it can even cause damage to the aircraft if the turbulence is very severe. Back in 2017, I covered a serious wake turbulence event where a Bombardier Challenger 604 was tossed around like a paper airplane after it encountered the wake behind a crossing Airbus A380. In fact, it was so severe that the Challenger was flipped upside down and lost some 9,000 feet before the pilots could regain control of it. And when they eventually landed, the aircraft had been so badly damaged that it was actually written off. But this is where things get interesting. So far in history, we've used the general understanding of the design of bird wings in order to get ourselves up into the air in the first place. And as I mentioned, we've also started to look at how specific components of their wings work in attempts to make our aircraft wings even more efficient. But now the industry, and especially Airbus, is starting to look into these potentially lethal wake vortices to see if maybe they could also be used for something positive. For this, Airbus is now studying the humble goose, or I should say gaggle of geese, and how they fly in each other's wakes. You see, geese, like a lot of birds, fly in formation, especially when they're out migrating, but geese do this exceptionally well. They actually managed to create an almost perfect V formation, which is estimated to increase their range by a staggering 71%. And this is made possible through 2 different mechanisms. First of all, for all but the lead bird, this means a decrease in wind resistance since the bird in front is effectively acting as a kind of windbreaker. But secondly, every time that a bird flaps, it creates a vortex, very similar to the ones created at the wingtips of airliners. And when this happens, the air directly behind them is pushed downwards, but the air behind and to the side actually moves upwards. So in that V formation, the bird behind and to the side gets a little bit of helpful lift without having to do any work themselves. And this trick, surfing the upwash, is also known as wake energy retrieval. So how can this translate to aircraft flight efficiency then? Well, Airbus thinks that it can be used to improve the fuel consumption and therefore efficiency of aircraft, particularly on long-haul routes. They estimate it will lead to around 5 to 10% improvement in fuel burn and therefore similar reductions in CO2 emissions, which is pretty significant when you consider the number of long-haul flights that could eventually benefit from it. When they started this project, it was initially known as Fellowfly, and I've talked about it before here on the channel, but the newly named project is known as Geese, standing for Gain Environmental Efficiency by Saving Energy. Pretty good acronym, isn't it? Almost like it was on purpose. So far, this study has been focusing on oceanic routes, and it starts at the flight planning stage with the use of a pairing optimization tool, which shows whether the specific flight can be paired with another flight in the system. If a match is found, well, then this is included in the flight plan so that air traffic control are aware. Then, when the aircraft are in flight, the pairings will be checked again, and air traffic control will coordinate with the crew to try and sequence the flights together. This will require both aircraft to reach a selected waypoint at a specific time and flight level. Once they are then in their correct positions, the leader aircraft will stay in contact with air traffic control, while the follower aircraft is then moved into their opti position, upwind to the lead aircraft, where they can benefit from the wake energy retrieval. Now, Airbus actually tested this concept in 2020 with a long-haul demonstration flight between Toulouse in France and Montreal in Canada, involving 2 Airbus A350s. It ended up saving some 6 tons of CO2 emissions, so there is no doubt that this wake energy retrieval idea can actually work. But of course, the logistics and safety of reducing the separation and moving aircraft into the correct position is what the next phase of Geese now needs to overcome. Currently, separation standards keep aircraft 1,000 feet apart in oceanic airspace, like the NAT-HLA, where this test is planned to be implemented, and they tend to also be 10 minutes longitudinal distance away from each other. But to benefit from this wake energy retrieval, aircraft will need to reduce that separation to just 3 kilometers or 1.5 nautical mile, which absolutely should be doable, but the big question is how to integrate it safely into multiple operations, particularly when we all know how risky the actual wake turbulence can be. One of the biggest concerns is that the ever-changing environmental conditions is going to cause problems, particularly over the North Atlantic, where there are increasing levels of clear air turbulence already. This will obviously have to be taken into consideration, since turbulence can require changes to cruise levels and speed, all of which will then impact the aircraft behind. Turbulence will likely also result in the shifting in position of the involved vortices, so managing all of this dynamically might be a real challenge. Studies of birds show that they have to regularly adjust their own flight path just a little bit to ensure that they remain in the good wake, and no one is entirely sure exactly how they do this. It might be just a case of them getting a feel for when things are right. But what this means for aircraft is that it might not just be as easy as dropping into formation and then just staying there. Instead, that opti position might vary, and the separation might become insufficient if local turbulence becomes too severe. So what this all means in reality is, at least initially, the fuel planning will not be able to change at all. Aircraft will still have to carry the fuel for this particular flight based on standard flying methods, in case the wake energy retrieval is not possible or if it's disrupted partway through. Another big challenge lies in the actual logistics. How will flight planning and dispatch be integrated with the pairing optimization system, and how will air traffic control actually manage the sequencing? This is not going to be simple, because currently there are a whole range of different flight planning softwares that operators use, and if this is to be successful, well, then the pairing optimization tool will have to be compatible with the vast majority of them. On top of this, safety parameters and contingency procedures in the event of technical issues and other problems will also need to be considered thoroughly. Currently, the contingency procedure for an in-flight emergency over the NAT-HLA is to turn 30 degrees off course, and once established at 5 nautical miles, in the case of a rapid depressurization or an engine failure, you descend. How this will be managed for aircraft with reduced separation will potentially need to be considered, and the same thing will also go for weather avoidance. You see, at the moment, aircraft needing to immediately avoid weather when operating in the NAT-HLA can avoid by more than 5 nautical miles, but must climb or descend 300 feet when they do so. Without three-way communication between air traffic control and the following aircraft, this will require some thought as to how to manage both the avoidance and also the re-entry into wake energy retrieval flight after it. Then there are, of course, the arrival procedures, who would also need to be adapted in case several aircraft would arrive at once into the same airport, to avoid several of them having to go into a holding and therefore lose some of the fuel gains that they've had. Because of all of this, the next trials will be critical for determining how aircraft can adapt their trajectories and what the process for airlines and controllers would need to look like. This is known as CONOPS, or Concept of Operations trials, and it will look at everything from safety aspects, general operations, to the impact of those legacy systems currently in use and the procedures ATC are familiar with. And Airbus is working with some big names in this trial. Air France, French Bee, Delta and Virgin will all cooperate under phase 2 of the Geese project to start tackling these questions and also begin to gather data in order to measure the practical efficiency of the concept. It's not going to be easy, as I've already shown, but there is a lot of motivation to make this work. Improving fuel efficiency and with it the environmental impact that the aviation industry has is a big business right now. So it's no surprise that the EU are adding around $11 million to the funding of the project, and there's already thoughts about how to extend the scope of the trial to incorporate other aircraft, like Boeing's for example. Now this will require even more study, because right now Airbus have all the data for their own aircraft, but the system itself will need to include data for any types wanting to participate in order to best determine the optimal pairings. Something that might prove challenging. You see, aircraft have different levels of susceptibility to wake turbulence, and their wings all have different aerodynamical profiles. And then there is the performances of the aircraft themselves and things like optimum and maximum operating altitudes, which will all have to be factored in. So a simple solution from nature is going to prove anything but simple when we try to use it within our own operations, but it might still be worth it. Anyway, in conclusion, Geese really are the main muse for aviation at the moment, but as we have seen, they are certainly not the only ones. Eagles, owls and even dragonflies are also being looked at for more biomimicry inspiration and innovation. And this is a good thing, since after all, nature tends to have a way of doing things right. But then again, how much we can then force nature to fit into our unnatural designs is a completely different question. What do you think? Is there an untapped natural design that we should be looking closer at? Let me know in the comments below, and please like and subscribe to the channel when you're down there. I hope that you also have had time to check out Ben's and my virtual Boeing 737 course. If you go to virtual737course.com, you'll find over 10 hours of detailed and easy to understand instruction from 2 experienced Boeing examiners. And if you use the code Mentour now, it will give you a 20% discount to the normal price. So check it out. Have an absolutely fantastic day wherever you are, and I'll see you next time. Bye bye.